Last section of our intro to trig unit here, and this is where it gets a little bit crazy. So we're going to cover two topics. I'm going to show you the proofs for them, but just keep in mind that when we're doing these things, we're going to kind of keep it at the high level. So I will show you the proof, but then I'll show you its application, and it's fairly easy to actually just plug in the numbers. So while these equations may look crazy to you, just keep in mind that we have the building blocks to get there, and then once we have established it, pretty easy to just plug in numbers and use it. So the first thing we're going to look at is area of a triangle. We're going to then take our area of a triangle and we're going to kind of transform it into this law of sines, and we're going to also have a law of cosines that we're able to use. So these two things are used to solve for lengths or angles, and we'll get there in a second. So let's start out with the area of a triangle. So when we're looking at area of a triangle, we can talk about the area of a triangle as 1/2 base times height, although we do know we have other ways of talking about it as well. So, we've done Heron's formula, but let's stick with our 1/2 base times height here. So what we're trying to prove is we can get a setup, so we get 1/2, and now these variable sides are interchangeable, so this is just like the generic labeling for this thing. This is not a right triangle, so just keep in mind this is just any normal, scalene triangles, the only thing we would assume here. And from here, the BC and alpha can be swapped out, so this could be A, B, and gamma. And so again, 3 different forms, but we're just going to prove the first one. From there, it's pretty much just adjust by picking a different side length. So we're going to start with calling our base B here. So since AC is oriented at the bottom, it's typically what we're most comfortable calling the base. So we're going to start out with the fact that we have the area of a triangle is 1/2 base times height. So knowing that I have 1/2 base times height, I basically just want to say, okay, well, what is the base and what is the height? Oops. The base for this thing is going to be B. So I know it's a little bit confusing that B and base are both B things, but roll with it here. So I'm going to use my base B here, and then I want to talk about the height. So what is the height of this triangle? The height of this triangle is from here to there. Now, keep in mind, it is not C and it is not A. So looking at this thing, I want to drop an altitude down. So this is the height of my triangle right here. So from B to AC, and it intersects at point D. So this point D has a perpendicular intersection with AD and BD. So 90-degree angle gets created here as the altitude drops down. And now I want some way of talking about H. So I'm going to choose to look at alpha here. Again, you can choose by looking at gamma. We're just going to stick with alpha for now. So again, you can rotate this, flip the side. There's 3 different versions of it. So we're going to stick with this one. So looking at alpha here to start us off, if I've got this alpha value and I've got this 90-degree angle here I've got a right triangle. So we have a right triangle with some length here and I have some height here. So in terms of talking about this height, I basically want to relate it to back into this equation with something that I can use. So the thing that I'm going to use here is I'm going to use choose another color. We'll use green. So I'm going to say that sine of alpha, whoa, that's an infinity sign, not alpha. I want to say sine of alpha is going to equal H over C, where C is my hypotenuse. So interested in this thing, using this thing, and this angle. So here I have a sine set up. So sine of alpha is H over C. So if I want to get H by itself, I'm just going to multiply both sides of the equation by C. So I get H equals C times sine of alpha. Now I'm going to take this and substitute it in for my H right here. So I'm going to substitute that value in. What does that look like? That looks like A equals 1/2 A, B, C, sine of alpha. And there is the formula we were trying to prove. So again, we can change which kind of starting point we're using. If I wanted to use gamma, I could have set it up that way as well, and I'd be using gamma and A. So if we want to swap these things out, again, another version of this would be 1/2 A, B, sine of gamma, and another version of this would have been 1/2 A, C sine of beta. So just keep in mind 3 different forms, just depending on where I'm starting and what angle I'm using in my triangle. So I can drop an altitude down like that, no problem, and I can also drop an altitude down like that, no problem. So that's how we get all 3, and they're all going to be equal because it's obviously just the area of a triangle. Area of a triangle is not changing. So now that we have a proof for this, let's talk about how to actually use it. So here, I'm just looking at a triangle, and here's what I'm going to try and emphasize for you guys is that if I've got this angle, which I am using, I'm going to use the 2 sides that are adjacent to it. So for this setup, I'm going to say this is my setup in red here for alpha. So again, using the alpha angle, and then the 2 side lengths next to it. 1/2, those 2 side lengths multiplied, times sine of that angle alpha. If I were to set it up using beta, then I'm going to be using the 2 sides adjacent. And so now here we see that. Last but not least, if I was using gamma, 2 adjacent sides here, and I'm good to go. So just keep in mind that it's pretty straightforward in terms of like plugging these numbers into an equation. If the proof itself is a little bit confusing, feel free to go back and watch that again. But ultimately, I'm just looking for application. So now let's try and use it. So here, I'm just going to start out by saying, here's the angle. Here are my 2 adjacent sides. And this is always an included angle. So this is trapped between these 2 sides. So I'm going to set this up as sine, as like a sine of alpha thing. It doesn't matter what you're calling these. I typically will get away from using B, C, and alpha, because then I'm gonna have to like worry about the naming scheme. And as soon as I change the triangle to like triangle CAT, people lose their minds because then they're like, I don't know what is alpha, what's beta, what's gamma. It doesn't matter, right? If I was using CAT and I wanted to do this, I would just say, okay, use this angle and then this side and this side. Oh, you don't want to use that one? Okay, use a different one. Use this angle and then use this side and this side. So it's always just the included angle between those 2 sides. So jumping back into this one, let's plug the numbers in. Doesn't matter which is which here. So 1/2 times 6 times 10 times sine 33. We're just going to round to the hundreds place here. As an exact answer, it would be 30 sine 33. But let's say, for example, I said round to the tenths place. This is what we would get. Not too bad. So looking at example 2 here, we're told that A is 7.6. I am told C is 10.2. And if the area of this thing is approximately 38.3, I want to find beta to the nearest degree. So right now we're just going to set up, and instead of solving for the length or solving for the area, because we can take any one of these pieces out, here we're just going to be solving for the angle. Okay, so as we look at this, I'm going to say my area here, 38.3, is equal to, and now here I'm going to set up my, let's see, what color have we not used yet? We haven't used blue. So we'll use our beta angle is blue. So 1/2, my first side here, which we'll say is 7.6, my second side here, which we'll say is 10.2, and then we've got our sine of beta. And now I'm just going to divide by whatever this stuff is as a number. So I'm going to multiply this stuff together. I think you get, what, 38.76. So I'm going to divide by 38.76, divide by 38.76. So now I have sine of, that always happens. There we go. Sine of beta is equal to, and I'm just going to leave it as this nasty thing, 38.3 over 38.76. So now as I'm looking at this thing, I'm saying, okay, well, how do I solve for this? I need to take my inverse sine and inverse sine. So my beta value is going to equal, and this is an exact answer, is inverse sine of 38.3 over 38.76. And now from here, I'm going to say, okay, well, what if I wanted to approximate it? It would approximate to about 81.16. So if it's saying to the nearest degree, just call this thing 81. And we're good to go. Here's where we get our law of sines. So our law of sines comes from the fact that we have all these areas that we can set equal to each other. So if I wanted to divide each of these by the same thing, that'd be fine, right? If I want to say times 2 times 2 times 2 here, that's okay. And I'm basically going to do that. So what I'm going to do is I'm going to divide everything by 1/2 ABC. And we'll see why that is in a second. Again, I don't expect this to be like super intuitive to you as to why it is that we're doing this thing. I'm kind of just pushing us in the direction we want to go. So I want a way of comparing these things that's easier, basically. So I just don't want to worry about having so many different variables. So I'm just going to divide out and have a more simplified version of this thing, which is our law of sines. So by dividing each of these, the 1/2s cancel off in each of them. That's pretty straightforward. And then for each, respectively, the b and the c are going to cancel off here, and I just have sine of alpha over a. So there's my first simplified ratio. Next one here, again, 1/2 and 1/2 cancel off, AC and AC cancel off, sine of beta over B. Last but not least here, we have our 1/2, AB's canceling off, sine of gamma over C. So this is, each of these angles is opposite the side length here. So like if I zoom back up here just for a moment, we see gamma is across from this little c, and it corresponds to the big C. So this C angle is using gamma as its angle across side, the side across from that angle is the lowercase of that. So here gamma goes with C, beta goes with B, alpha goes with A. And we see that right here as well. So in these triangles, basically that's what we're looking for, is I either need the angle and the side across, or one or the other, and it's provided for another set like that. There are some traps that we run into with our law of sines, but we're not going to cover them. Basically, this is where we have this case where we have like angle side side. So again, if you wouldn't write this on your grandmother's fridge, you would not want to use this in proving two triangles congruent, and we don't really want to use this in solving two triangles either, and this is the reason why. So I'll just very briefly talk to this point, but then beyond that, we're basically just going to leave it because we're going to say this is our intro to trig. We don't need to do anything crazy. So angle side side here, what does that give us? Well, here is a fixed angle, okay? So this orange angle here is fixed. I'm going to say this red side length is fixed, and I'm going to say I have some yellow side length which is fixed as well. I'm going to copy this here. Is this copy and this is paste? Yes. Shortcut keys for the win. Here we go. So looking at this thing, I'm going to make a case that instead of it looking like this, that I can take this and swing it out in a different way, and it's still going to complete a triangle for me. So I'm going to take the same length, I mean imagine that's the same length here, and I'm going to swing it in like this instead. So here I have one triangle I would say is the bigger triangle, and the reason I didn't fill this all the way in is because I don't have a fixed length for orange. So here again, didn't have a fixed length for orange, it's just going to be whatever's left. So in this case, I have given you an angle, given you a side, and given you a side. Given you an angle, given you a side, given you a side. And it forms two different triangles. For this exact reason, we can get into a few difficulties when using our law of sines, in that it will indicate two different triangles. There's not one that's right and one that's wrong, it's just that two are possible. So again, it's not that this is like wrong, other than it's funny to use angle side side, but this is just highlighting the fact that it is ambiguous here. So it'll be ambiguous here as well. If you didn't follow along with this, totally fine. Don't write this on the fridge. All right. As we look at this, we're saying, okay, in any acute triangle, there are three ratios for these law of sine things: sine of alpha over A, beta over B, and then gamma over C. So when we look at these things, if you wanted to flip them all, you could. It's just, you know, the reciprocal. So reciprocal is going to be true for all of them. So when we solve a problem like this, what we're going to do is we're going to take two at a time and set them equal to each other. So we're not going to be dealing with like a chain of equal signs here. We're just going to basically say, okay, I want to start out with these two, and I want to solve for whichever one is missing. So maybe I'm missing alpha, maybe I'm missing A, maybe I'm missing beta, maybe I'm missing B. One of these four things will be missing, and with the other information, I'm able to solve for it. And once I do that, I then say, okay, maybe I want to do my gamma and C. So now I want to solve for this. So when I do, again, I'll set it up using one ratio set equal to the other. So it's not that, we're not using them, just that we're not using them all at once. So we're just doing two at a time. And it's always sine of the angle over the length of the opposite side. So let's actually do one of these things. Now, I don't particularly love this just because this is a little bit of like a harder version. I think this one's a little bit easier next. Yeah. But that's okay because we're strong in algebra, so we can figure this out, no problem. So looking at this one here, I'm going to color these things. So I'm going to call S red, and I'm going to underline this in red. I'm going to say R is green. I'm going to underline X in green. I don't really need to do this because I don't really want to, but I'm going to at least just underline T, and I'm going to just put a lowercase t here because that's what that would correspond to. So looking at this now, hopefully that's not confusing with the X. So looking at this, I'm saying, okay, well, I know this angle and this side length opposite. So I definitely want to utilize this in using my law of sines. Now I'm trying to solve for X, and I know this angle opposite. So I want to now be using R and then what would be little r, what we're calling X here, as a variable to solve. So in setting this thing up, I'm going to set it up as sine of 45. What the heck? That's not 45, that's 44. Never happened. What on earth? Heaven help me. There we go. Divided by, and now I'm going to say this side length, which is 10. And now I'm going to set this equal to my green thing here. So I'm looking to solve. Here I have sine of 60 over, and now here I'm going to use my X value. So I want to get X by itself. What am I going to do? Well, two things you can do. One, you can think of this as multiplying by X and then dividing by this stuff, or you can cross multiply and then divide by sine 45. It doesn't matter which route you go, you're going to get to the same spot. I'm going to use this entire problem as sine 45 and sine 60 until I get to the end, once I've got X isolated. Then I'll start changing what sine 45 and sine 60 look like. So the first thing I want to do is pick a new color, so blue. So I'll cross multiply. I don't know, I feel like most people are most comfortable with that. So let's call this X sine of 45. Please keep in mind that sine of 45 is just some number, right? So this is just some number. It's not like saying I have X times sine times 45. That's not what this means. This is just sine of 45 equals 10 sine 60. So now as I look at this thing, I want the X by itself. So what am I going to do? I'm going to divide by sine of 45. So in doing so, I get X is equal to 10 sine of 60 over sine of 45. So this is my exact answer here. We can come up with an approximation for it, but we can also keep this exact because sine 60 and sine 45 will give us exact answers. Now, I don't, again, expect you guys to remember this, and we're not doing like a full-blown, this is not a full-blown trig class, this is just intro to trig, so I'm not expecting you to have these things memorized, but sine of 45 is root 2 over 2, so I'm going to write this as root 2 over 2, and my sine 60 is actually root 3 over 2, so I'm going to say 10 root 3 over 2. So could I, if I gave you, this value here and this value here, simplify? Yeah, absolutely right. So on top here I got 10 and I got 2. I would say cancel this off and say I got 5 root 3 divided by, now on the bottom here I have my root 2 over 2. So now I'm going to say I've got 5 root 3 over 1 times 2 over root 2. As I look at this thing, I'm just going to simplify. So I get 10 root 3 over root 2. This is going to simplify by multiplying by root 2 over root 2 and rationalizing my denominator. So I'd be left with 10 root 6 over 2. I simplify one more time, and my final answer is, I'm just going to write it down here, 5 root 6. So just simplifying that right there to be 5. So final answer here would be 5 root 6 for my x value, which is the length st. If I gave you guys this problem, I'd probably just say round to the hundredths place for that value. Look at example 4 here. So let's label these things. B is going to equal 12. We're going to say C is 10. And we've got beta is 83. So the reason I'm doing this beta angle in red and this side opposite is because those are going to correspond together. So here we're going to set this up as sine of 83 over 12. And then my goal here is to find gamma. So gamma is going to be right here. And now again, I'm just going to do my sort of algebra part here. All the geometry is done. So now I'm going to say we'll multiply both sides by 10. So I get 10 sine of every time, I'm telling you, 83 equals gamma, oops, sine of gamma there. And now when I look at this thing, I say, okay, well, how do I get gamma by itself? I'm going to take the inverse sine of both sides. So my final answer here is going to be that gamma equals inverse sine of 10 sine 83 over 12. And then we can approximate this answer as well. So we get this thing is roughly 56 degrees. So when we're looking to solve for gamma and we're just rounding to the nearest degree, then we're going to say gamma is 56 degrees. I don't know, I'm tempted not to mention this, but I'll mention this. So when we're looking at this, keep in mind that maybe this thing swings out in such a way that it could create two triangles. So in this one, I don't think that it does because this b value is greater than this one here. But if these two values were swapped and we solved our answer, again, this would be kind of like our ambiguous case. So again, staying with the simple ones, this is all I need you guys to do, but just keep in mind that in the future, things will be more complex, but you won't really see that till trig class. Law of cosines. Okay, so I know this seems like a crazy proof, but it really, really isn't that bad. So the first thing is just saying blah, 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 law of cosines. We're going to use this basically by just solving for, I mean, this whole thing is how to read off the law of cosines. It's insane. No one thinks about it that way. So when, again, I'm looking at this, I'm saying this thing, this angle is opposite from this side, and I have this adjacent and this adjacent, and that's how I set up this formula. And that's going to be this one right here. So this is the one by itself over here. This a squared, oops, I'll circle this one. So that's the one by itself. A squared, b squared are the ones next to, and then here's my angle that I'm using. And this is, again, just my a and my b value. So it seems super crazy, but again, once we prove this, we're good to go just using it, and we're just going to be plugging in numbers. So it's really not that bad. So let's actually look at proving this thing. So when we're looking at this, basically we're trying to set up our law of cosines here, and we're going to use this to find unknown measures in a triangle. That could be side lengths, or it could be angles. It depends on what information we're provided. So let's look at this. Starting with this triangle here, I want to say, okay, I just want to prove this thing. And again, I'm going to definitely push us in the right direction of like how we're going about doing this. Looking at this, it may not seem apparent that that's, you know, even an attainable goal sort of thing. So looking at it, let's start out. I want to talk about the height of this triangle. So again, if I wanted to talk about a relationship within this triangle, if I had a right triangle, I know Pythagorean theorem applies, so I get this relationship with Pythagorean theorem. So I'm going to set that up, but I'm going to set it up for two chunks. The first chunk I'm going to set it up for, and this is with the altitude being dropped down, so let's drop this altitude down. So n is the altitude here. Again, scalene triangle, doesn't matter, nothing fancy about this. So altitude drop down, that's from B to D, and we're going to call that length n. So our height here is n. I'm going to say this chunk over here is something, and that something is, I'm just going to name it m. Okay, this whole length on the bottom was b. So if this whole length was b and this chunk is m, then that makes this chunk here b minus m. So we've done this a few times. They're just, segment addition postulate basically coming into play here. If this whole thing is 10 and this part is 2, that means this part's 8. If this whole part was 100 and this part was 50, that means this one's 50, right? Now, again, that would be kind of a special case for isosceles triangle, but I'm just saying take the whole thing, take out this chunk, what is left? So now I have established these lengths in orange, green, and red. I'm going to highlight them below here in orange, green, and red for you. So whenever I talk about the legs of a triangle, I also want to include the hypotenuse. So we're going to do A here. Whoops, not in black, in blue. So I'm doing A in blue. There we go. And we'll do C in purple. So again, just focusing on the two right triangles B, D, C, and the right triangle B, D, A. So first starting with the one on the left, so we got A, N, and M here. So in this triangle, I've got, again, my M value. And so this is the triangle on the left there. So this triangle is just saying leg squared plus leg squared equals hypotenuse squared. Cool, that's all it is. Here I'm going to say the same thing. Leg squared plus leg squared equals hypotenuse squared. So let's color in those values here. And we're good to go. So now as we look at this thing, can we rearrange our variables to maybe do some substitution? Yeah, there are multiple ways we could set up this substitution. Let's just do it for m. Okay, so let's get m by itself here. So when I'm looking at m here, how do I get m by itself? I'm simply going to subtract off my n squared value. So here is my n squared value now, and I'm going to be using this to substitute. Now I want to actually FOIL this thing out. Please, please, please know this is not just b squared minus m squared. That's not a thing. It's never been a thing. It will never be a thing. Okay, we have to FOIL this out. So this red thing here is going to turn into this chunk right here. I don't think I need to write this out, but I'm going to do it anyways, just in case. Because it's fun. FOILing's fun. First term and first term, what the heck was that? Gives me b squared. My outside term gives me negative bm. Inside term gives me negative, terms give me negative bm. And then my last one here will give me plus m squared. That is where this is coming from. B squared minus 2bm plus m squared. So just FYI, FOIL, cool. All right, on to the next one. So now again, I'm just filling in these other values. So n squared stays n squared, c squared stays c squared. So all I have done is FOIL that thing out, nothing crazy. So now I want to look at this and I want to say, okay, well, as I look at these values, I kind of want to do this substitution in for my m value. So instead of writing it as m like this, I want to call this thing a squared minus n squared. So this chunk here is now getting substituted in. So I'm going to highlight the fact that I now have m squared here, and I'm going to be substituting in for that value. So that's where this is coming from. A squared minus n squared. This I'm going to just change to be like a squiggly line, because this is no longer talking about bm, or excuse me, b minus m. This is now just a chunk of that. So it kind of started like this, but it's definitely different now. So if I were to include this whole thing, it would be this right here. So that entire chunk is b minus m squared. So just keep in mind we did some substitution. It now looks a little bit different. N squared is still n squared. C squared is still c squared. Well, what's going to happen? I'm going to have some terms cancel off, right? I have negative n squared and a positive n squared. Those are going to cancel off. As I look at this thing, it's going to simplify to c squared is equal to a squared plus, and now here I've got b squared, and again I'm going to use a squiggly underline here because we technically were using kind of like a different underline before when we're talking about red specifically. We were talking about b minus m, and now we're talking about b itself. I guess I should maybe just change colors altogether, right? We have the colors. Why be stingy with the colors? This is now purple. Hopefully you can see the difference between indigo and purple here. So b, this full distance here, I'm going to say is purple. So here's my b value squared here. So now when I'm looking at this, I'm looking at this value, and I'm saying minus. Now I've got b times, and we didn't really have a color for m. Oh no, we did. Green. There we go. So now when I look at these things, I don't really want to leave this as an m value. Nothing really fits with m because it's just a portion. I don't know where that portion is going to drop down. So what I want to do is I want to think about, well, how can I kind of change this thing a little bit using either my, information about sine, cosine, tangent, whatever, my trig knowledge to do this. If I just focus in on what this m value is, I'm going to draw a triangle here for you. Let's do this thing. This, we'll even orient it the right way. So there we go. So looking at this triangle, I'm just going to fill in these lengths real quick here. This is, oops. So m is right here. I'm saying this height here is n, and then this is my gamma angle. We didn't really have a color for gamma. I don't know, we'll do it in pink. Okay, so this is my gamma angle here. Now this being a right angle, I should be able to set up some sort of trig stuff here. I'm also going to label this as A. So now looking at this triangle, if I wanted to set something up here, I'm going to set up with cosine. And the reason I'm setting up with cosine is I kind of want this thing to disappear, and I don't want it in terms of n. I don't want it in terms of m. I just want to talk about things in terms of A, C, and B. So that's my goal here. Again, it may not seem like intuitive why it is we're doing that, but hopefully at the end it kind of like all makes sense. So looking at this here, there's a relationship which is going to be cosine of gamma equals, so now here's my adjacent over hypotenuse, m over a. So if I wanted to isolate one of these variables, and I'm pretty interested in isolating m, I'm just going to multiply both sides by a. So m equals a times cosine of gamma. This is now going to get substituted in for my m value. So now this is going to fill that spot right there. So what am I left with in my final equation? Well, this is going to cancel off, right? So if I have my m value being substituted, this is now going to be minus 2ab cosine gamma, which we see right here. And we have reached our final form. This is the thing that we set out to prove. So again, may not seem totally intuitive how we got there. Hopefully you believe the math checks out, because this is all math we've done so far before in terms of like substituting stuff in. 2 plus 2 equals 4. Maybe you don't understand why you're adding 2 and 2 together in the first place, but hopefully the actual process can be followed. So again, this is our law of cosines. I know it seems like a lot. If this is super confusing for you right now, again, I'm going to make it easier in just 1 second. I do just feel it as my math nerd duty to at least show you the proof for it. So I'm not just giving you a formula. It works, trust me, believe me, or follow along for yourself. Hopefully the latter, but I'm a semi-trustworthy math nerd. So here we go. Let's look at the length of AB in this triangle. So I'm trying to find AB. So in terms of this length here, I'm just going to call this red C, and I'm going to focus on this red angle C here. The other two things, I don't really care what they are. Here I'm going to just box it off in orange, and here I'm just going to box this off in green. I'm going to write out my formula, but I'm not going to use any of these C, A, B, values or whatever like that. Or I guess I will, but I'll just color them. So again, I kind of want to stay away from naming things with like A, B, and C, because people get super thrown off and they get like obsessed with what value is what. So as soon as I name this triangle DOG, you like lose your mind, because you're like, I don't know what A, B, and C are. I don't know what alpha, beta, gamma are. So again, I'm trying to stay away from that, but I will start out there and color code this thing. So let's look at this and let's color it. So the thing that I want to first point out is that the side length, which is being isolated on Misfit Island here, is the same as the angle which is being utilized, right? I'm using side length C over here. This is using angle gamma, aka angle C, right here. So those two are on opposite ends of the equation. Everything else is just anything else next to it. So here, it doesn't really matter which is which, but I'm going to color it accordingly. This is my B value right here for 4. Here's my B value coming into play again. Here's my A value here. Here's my A value coming into play again. So that's my formula plugged in here. Again, I try not to focus on A, B, and C, but this is ultimately what the equation is. If you want to always relate it back, feel free to do so. So now let's fill in some values. I don't know what C is, so I'm going to leave it as C squared. Let's do equals plus minus 2 cosine. There we go. So I'm going to also name this cosine as my 30 degrees. So just trying to keep the neutral things in yellow here for color coordination's sake. My A value here being squared is 4 root 3. And that's being squared. And then I've got, oh, there's no way I'm going to be able to fit that stuff in there. Not even close to enough space. There we go. So 4 square root 3 there as well. And then let's get our B value at the table here, which is 4. That thing is squared. And we just have 4 here. Okay, so I've now plugged in all the values and one is missing. Cool. So I can solve this side length missing opposite from this angle, or if I change things up and I knew this side length, I'd be able to solve for this angle. So just keep in mind that's the other kind of like flip of the coin when we're doing our law of cosine stuff. And we'll see that. Yeah, we'll see that next. Perfect. So looking at this one here, now I just want to basically do the math out. So let's do it all in blue. So when I have 4 root 3 squared, it's going to be 4 squared, which is 16, times 3, which is 48. Here I have 4 squared, which is 16. Here I have minus, and now I'm just going to write this as the value itself, and then I'm going to say times cosine of 30. The reason being is I don't want to simplify or lose any of my, I don't want to start approximating. So 4 times 4 is 16, times 2 is 32. So I'm subtracting 32 root 3 times cosine of 30. So again, all this stuff is being multiplied. One of the biggest mistakes I see people make is that for some, I don't know, some odd reason, they start breaking this out, right? This is not being broken out. This is all being multiplied together. You're not subtracting 2 and then just, able to add 2 to the other side. It's subtract 2 times A times B times cosine gamma. So this is all one chunk. So if I wanted to solve for a gamma thing, I'd have to divide by this chunk here. So now I'm saying, okay, well, C squared equals all this nonsense. So when I'm looking at this value here, my cosine of 30 is going to be, trying to think, it's my root 3 over 2, yeah? So when I do this, this is going to simplify. So again, I don't expect you guys to know these things. Root 3 over 2. If you wanted to use a calculator and just approximate this thing, that's totally fine. They'll end up canceling off regardless. So if you just punched in your calculator, you would never know the difference. So what do we get? 48 and 16. I don't feel like doing mental math here. 64. So now when I multiply this out, this is going to end up giving me, what, 48? Because this will give me 3 and 16 times 3, yep. So 64 minus 48 should give me 16. Take the square root, and I'm only going to keep the positive one. The reason I'm only keeping the positive one is that I cannot have a negative side length. So here now we see that we had an isosceles triangle all along. Cool. We would have also maybe recognized that had we dropped an altitude down here and we saw this is a 30, 60, 90 triangle. But again, I don't expect you to see that. I expected you to do law of cosines here. So here we solve for our C value, which is 4, and we're good to go. So in terms of takeaways here, I would say just the biggest thing I'm trying to get you guys to understand is that this angle is going to be opposite from the side length, which is on the other side of the equation, and the other two are just going to be used throughout the equation. So it doesn't matter which is A, which is B, although this is labeled A and B here. So I kept the color coordination the same. I don't know anybody who does this, but if you want to use this alternative form of the equation, this is just to isolate the cosine value. So that way you can just do inverse cosine of this thing to solve for it. I always just use my original equation and then I go and just do the algebra for it. If you want to do this, go for it. I don't know, maybe it's like ever so slightly faster if you do that, but I just see too many people make mistakes by doing this, so I don't recommend it. Here it is for you if you want to check it out. It's literally just algebra steps. I mean, calling this a proof is pretty generous. This is just basically some algebraic manipulations. How do I get cosine by itself? Subtract this junk. Okay, then what do? Then I divide by this junk. Okay, well that's all this is. So just keep in mind that this is a thing. If you want to use it, go for it. I'm not going to. Looking at example 6 here. So now I'm, again, going to label these things in colors, staying away from A, B, and C. I don't even want to pay attention to what these are. I'm not going to use the right notation for that stuff. I'm going to use colors. This is next to it. This is next to it. So how does this get set up? This gets set up as 6 squared equals, now these two things, 4 squared plus 5 squared minus, I don't know, I'm going to change the color of the 2 just because it doesn't go with the green side length here. So minus 2 times 4 times 5 times cosine of beta. So now that I have this thing set up, I want to solve for cosine of beta. What am I going to do? Well, this becomes 36. This is 16. This is 25. This is going to be 8 times 5 is 40. Cosine of B. Please, 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 I don't know why people do this. Don't do this. This is all being multiplied, okay? This stuff just being added and subtracted, cool story. This is being multiplied, so you can't just add 40, or subtract 40 in with this stuff to solve your problem. So here I get 16 plus my 25, so I'm going to subtract off, what am I doing, 41? So subtract 41 from both of these. So I get negative 5 equals negative 40 cosine of beta. And now I'm going to take these two things and divide by 40 on both sides. You could simplify this to 1/8 if you want to, but I'm just going to leave it as it is sort of deal. I'll cross off the negatives, but beyond that, I'm just going to leave it. So now I'm going to say 5 over 40 is equal to cosine of beta. How do I get beta by itself? I need to do the inverse cosine. So beta is going to equal inverse cosine of 5 over 40. If you punched in 1/8, it's going to give you the same answer anyways because it's just simplified. And we would say that's approximately 83 degrees. And we're good to go. Here's a nice table that kind of helps run us through when to use each of these things. Basically, if I have 3 sides known, I'm always going to be using law of cosine stuff. So there's no way I can even set up a law of sines without an angle and the side opposite from it. So with just knowing 3 sides, not much I can do there. So again, this is like, I know these things, and I want to solve for that thing. So in that case, I'm going to use my law of cosines to do that. For my second situation here, the known things are A, B, and alpha. So alpha is known, A is known, B is known. I want to solve for beta. This looks to me like I got some information across, and here I have some complete information across. So this is going to be a law of sine setup here. For this one here, I am given AB gamma, and I'm trying to solve for C. In doing so, this is going to be a law of cosine setup. Again, I know 2 of the sides and I know the included angle. So this will be a law of cosines. Last one here, I am given A, alpha, and beta. And I want to solve for this side length over here. In this situation, I'm going to be using my law of sines to set this one up. So again, I know these 2 right across from each other, and I know one of these. So I can use that to solve for the missing one. Last problem here. It's crazy. All right. So we're setting up a child's swing set. Each of the 2 metal posts support a top bar is 8 feet. So at ground level, the posts are 6 feet apart. Let's make a triangle out of this thing. Eight and 8 and 6. So this is my given information here. From here, the alpha that I'm trying to solve for is, there's going to be the angle that I'm trying to solve for. They named it alpha here. So the angle, I'm going to just use theta. So again, I'm trying again to break us out of the habit of using alpha, beta, gamma, and I'm just using theta because this is the angle that I want. So the problem asks, what angle should the 2 metal posts be secured? So we're securing this part right in here. So to do this, I'm going to set it up with, you guessed it, colors. I don't know what this thing is, but I know it's adjacent to my angle. And I don't care what this thing is either. And when I say I don't know, I mean I know the length is 8, but I just don't care like what A, B, or whatever is. So I'll do this in green. And we haven't used yellow yet. Let's use yellow. Angle, side opposite from that angle. So the setup here is going to be 6 squared is equal to 8 squared plus 8 squared minus 2 times, I don't know why I'm using yellow here. I should have used another color. It's the one constant. It's like annoying, right? Because it's like I don't want to use the same color because then it gets confusing. So I don't know. It is what it is. 8. And now here I'm going to say cosine of theta. So I want to solve for cosine of theta. What am I going to do? Well, I'm glad that you asked. 36 equals 64 plus 64 minus 128 cosine of theta. So I'm going to subtract over 128. So let's see, 36 minus 128, negative 92. So again, subtracting off 128 here. And so I get negative 192 is equal to negative 128 cosine of theta. To get this by itself, I'm going to divide by negative 128. And now I get my theta value is equal to inverse cosine. So I'm going to take inverse cosine of that 92 over 198. Again, feel free to simplify it if you want to. I know the calculator is going to do this for me anyways, so why am I going to waste my time simplifying? So I look at this, and my theta value is approximately 44 degrees. And we're good to go. That is the conclusion of our introduction to trig. Good stuff.